and remove, and this one as well. Yeah, hi. So today we will be talking about backdrop, and I'm pretty much aware that most likely you learned about it in your previous study. Still, I think it's good, if not to learn it, I mean, from scratch, but even to refresh the knowledge, especially. So here the focus is on really internals of implementation. So not on how to use it, but rather on internals of implementation. And can you please help me? Can you shut the door? Thank you. So in lab 2, so I can comment right now that the main idea is that you really follow the implementation. So it's not by any means unique or best ever implementation of backdrop, but I found it very detailed. So once upon a time I found it somewhere, and I remember, so I wanted to understand really how to approach programming. So so this transition from specification to programming, to me, is I mean, it is where the complexity resides. And so today, so I want to go through again details of implementation, again focusing on really the math behind multi-layer perceptron, or in general feed-forward networks, neural networks with feed-forward error-correcting neural networks. So. Neural networks. And importantly, artificial neural networks. So we talk about this type of networks in the context of supervised learning. So context supervised learning. Where the truth is available for us during training. Also in the context of solving classification problems. Or categorization or discrimination. So it's a discriminative model. And but also in the context of representation learning. So at the end, what this type of network is good for is that they learn distributed representations, or if you wish, embeddings of otherwise unstructured inputs. Representation learning. And the input to this type of network, well, is a phenomenon that is described through a vector of its characteristics or its properties or features. And the number of such features can be large, depending on what you're learning. This is a feature. So the ground idea is that a category or a class can be modeled as a weighted sum of these features. And well, there is also a non-linearity involved, so in this model. But again, so this in the simplest way, so we are talking about the following. The following architecture. So you have input x1, xn, and then you have a function, so-called activation function, and so this attributes or features. So they so this function takes these features as an attribute and weights m, and it at the output it produces a score. Score of a class. And so this, I mean, the idea is that, so this is the activation function, as I said. So it is linked to biological phenomenon where neurons, so neurons are activated as a response to specific stimuli. So again, so here we have the inspiration, inspired nature. So we create a model based inspired by certain biological behavior. But again, so mathematically, we are talking about this kind of ground model. So also, so we have this function of act, and so this function takes weighted features. So all n of them. And again, just to be consistent, I mean, further I will use this act to denote the function. So it will be a function, activation function. So, and then of course we want to generalize this kind of ground model to include higher level interaction between features. So it's not that first of all we have we should include the possibility of having several classes, so not a single one, obviously, and then also address the cases where address the case of our understanding that a score of a class is or the structure of classes can be complex, and so interactions between different features result in kind of contribute differently to a computation of score to a particular class. And so the generalized architecture idea is it's simply that we stack this architecture, we expand it, but all in all, so the ground principle is same. So we have x1 to xn, and then we have activation functions. And maybe again, so to account for more complex interaction between the features, so we may further expand it. Etc. And finally, so we want to compute the activation classes or the functions that produce the score. Score for class 1, score for class M. But the idea is that so we try to kind of take into account all possible interactions of features. And so that's a second level interaction, basically. And so on and so forth. And finally, so everything contributes to calculation of the score. So this kind of complex structure. So we have input. So we have output here. And we have something that is hidden or hidden layers. Right. But then we thought, you see, all in all, we are talking about mathematical model for a given category. So we a function that actually so the ground model is this. So we want to have a function that transforms features, maybe unstructured, into certain number. And so this generalized structure in this case mathematically is very complex to describe by a single equation, and that's why so people normally adopt this kind of graphical representations. But if we just, for example, focus on a single branch of this pipeline, then so what we have here, so we basically so our output for a single branch. So our output is a kind of nested activation of functions of the input value. So it's activation of some weight multiplied by activation and another weight. So let's use this Roman numbers for latest. Of activations. And finally, so here we have, say, the reverse order of the activation of the first order on the input. Weighted input. Input. So nothing more than that. So just a function of functions. And so another constraint or actually property is that this function should be kind of nonlinear. So again, so why it was decided to be so well, reflecting on the fact that most of the problems or data described by data have a nonlinear character with respect to separability. So you remember we discussed it when we talked about SVM. So a problem, again, from the point of view of data, may look as a very, very complex surface, which is called manifold. So, and to address it, so essentially, if you look at this formulation, so we transform an input in some way so that we at the end we are able to kind of separate one cloud point point of cloud of points from another cloud of points. But something is missing here. So this is a computation of a score. So what we are missing here, it's a model, it's a data-driven model of a category. But we are missing this error correction. So to correct error, so we need a kind of a measure of our satisfaction that this output is actually something that we want to have. So we need a measure of quality of the score. And this measure is captured by yet another function. So which is called cost function or loss function. Synonymous with cost function. So it is a function. So well, it can be denoted differently in different sources, which basically takes this output score and compare it to ground truth. Oh. Well, roughly speaking. And so it is this function that we use to judge how good our model is. So the learning is actually about correcting errors. So if this function tells that the outcome, so the score, outcome of this computation above, so for a given input, doesn't coincide with the expected value, so with the truth value, then we need to make adjustments to it. So we need to change somehow the output score to make this measure better. And this is done by actually adjusting this weights parameter. So this is the only parameter. Well, we also have this bias, but I mean, in the first approximation, just weights, which interacts with data, or it in the first place, in the very beginning, it interacts directly with the features, but then also, so the farther we go, so we have next level interactions, which are also weighted. So adjusting these weights, we actually we actually may improve the quality of the model. And to do that, so we want to take the derivative of the model. So this would be our final formulation. So to understand this adjustment, so we take the derivative of this model with respect to specific to the weights. So, so here we have this multivariable function, as you see, so with the different variables, v1 through, well, v3, but we have many weights. So we want to understand how our function is sensitive to change of each and every weight. And this is captured by this partial derivation. So, right? So we basically compute these derivatives of this function with respect to all weight parameters that we have. Begin and use it. Use these gradients. So this partial derivative is also referred to as a gradient to adjust the weights. And this is our learning. You remember? So as we discussed yesterday with some, so learning, and in this case it's error correction learning, is about adjusting the weights. So W mu equals to, well, the old value minus learning rate, derivative of cost function with respect to this weight. Clear, right? So that's the standard formulation. Now we go into some. So this is still kind of high level problem formulation. So now we need to put some meat on the bones, so to say, and see how this derivative look like. So for the actual implementation. So that's what we need to compute, and then we will come to the very interesting outcomes, so to say. So first we need to decide so what kind of activation function we have. So here, in principle, we can use any non-linear and differentiable function. So that's it can be a non-linear differentiable. Differential function. And historically, so it just it was identified maybe, I guess, mathematically. I mean, based on mathematical backgrounds of people who work with this technology. Maybe again with some desired behavioral functions, but also which appear to be possessing interesting properties from computing point of view. So the three types that are used in the context of neural networks are sigmoid, so it looks like this. So, the sigmoid of X. So it's a 0, 1, and 0, but then smoothly goes to 1 like this. It is defined as sigmoid X 1 over 1 plus e to the power minus x. And but what is practically important to us is how we can compute derivative of this function. So a derivative of sigmoid of x with respect to actually here we are not talking about partial derivatives. Dx. That's quite interesting. It's sigma x 1 minus sigma x. So if you do this derivative, so then at the final stage you will see the term which is corresponds to the initial original function 1 minus original function, and then this, along with the other functions who have similar behavior, is actually used to streamline, for efficient computation. So you compute. So maybe I forgot to mention while being on this level. So we can identify two directions of information flow. So the forward direction where we compute the score, and then the error correcting direction. So when we try to do adjustments in order to change the scores. So, but the reverse direction, so in the backwards direction, so we compute derivatives. So that's what I say. But the interesting thing is that this derivative in the backward direction can be computed immediately when you do forward computation. So that's so you don't do extra computations for the backwards path, so to say. And this is what I want to what I want you to observe in this implementation of that is given to you in lab 4. No, 5. In lab 5. So you are given the implementation of perceptron, and so have a look how it is done there. So next, the next function which is used is hyperbolic tangents. So it looks like this. So from -1 to 1. And again, so it's it has the following shape. Yeah. So, and again, so it is defined as the tangents e over x minus e minus x, and e x 1 E minus x, and the derivative of this thing dx is 1 minus 1 squared. Okay. So once again, same thing. So you compute it once, and then I mean, while computing the forward way, you immediately can prepare for backwards propagation of the error. And third type of function that we can use is something which is called ReLU, which stands for rectified linear unit. So looks like this. So this is x, this is real. So it's all zeros for negative values of x, and then so x is x. So preserving all positive values basically. And so real no x. So, and then so we need to define derivative dx. So it's either 0 or 1. So for non-zero values. Yes. So next thing we want to load with some details. So that this type of activation functions are used on all these stages, like hidden layers and score computation. But then we need to do some extra stuff, and roughly speaking, we want to normalize. We want to normalize the output, because so if you don't do that, well, you actually may live with even with these functions if you wish, but then you need to take some extra measures at the output. But one extra function that you might need at the end. So if you have this activations, final level activations, which result in scores. For m, so we have this m is the number of classes. M is number of classes. So what we want to do, we really the only thing we want to normalize it in count. So that's and one way of doing that is to normalize it such that the sum of the outputs is equal to 1. And this is done for further usage of these values of this property in connection to a special type of the cost function. So basically we need normalization. So it has same number of outputs as inputs, but so what we want to have, so we want so let's call it PI. So we want that the scores, they could be interpreted as probabilities or percentage of belongingness to a specific category, one to through n. So it's a interpretation. So probabilistic interpretation. And so for this purpose, the function which is used here is called softmax. So it looks like this. So it's S. Maybe I can. No, sorry. P1. So S. And it is equal to the following. So you rise f of xi. You rise exponents to xi and divide by sum of I. That is j. J was 1. So this is the definition of softmax function. And yeah, what is missing here? Yeah, well, what is missing is the derivative so far. So need to compute derivative. So let me see. Maybe I can see this one and rather concentrate on something different. Let me see if I have forgotten something. I will show you the starting point again. So I find it personally super interesting to really trace the whole way down to the end manually. But now we will do some shortcuts. So the starting point to compute the derivative in this case, well, it's we have a division here. So you apply the rules for taking derivative for division, but so if you do all these computations, then partial deliverable the derivative as x j. So it's a sorry, so here it's x j. Here by dx k equals the following. So it's s of x j 1 minus s of x. So again, so it's very kind of useful computationally friendly function. So you can compute you can easily compute its derivative, and that so this form is valid for k for the case k equals j. and then minus s of x j multiplied by s x k. So for k not equal to j. So I mean, just useful to remember this thing. So now we are equipped with pretty much everything except for the cost function. And so there are different cost functions you can choose from. So in the simplest case, you can use mean squared MSE, mean squared error. Why not? So there are other functions. So basically, what you want to compute a distance somehow. So from the outcome of the computation on this final stage to the truth, which is encoded somehow. So normally, so you know that. Again, there are probably different approaches. So typically, one use one-hot encoding style. So when you have a vector of the dimensionality equals to the number of categories, and so the category, the target category is marked, or the true category is marked by setting 1. On the position, on a certain position. Yes, but as such, so you can basically compute the distance already based on this outcome to this one-hot encoding using pretty much same using pretty much any distance function. The only thing is that you need to compute the derivative, and that's the whole thing makes it different. And now, so I found it very interesting to trace, for example, why one of the functions, the cost functions used in the context of backpropagation is a so-called cross entropy. So cross entropy as a cost function. Actually, the choice of this cost function, so it makes sense only if you do this kind of normalization. So, so if you have this property that the output sums up to 1, this gives us a possibility. So, it's pretty much a kind of artificial step that you can treat them as probabilities, because simply mathematically they possess this property. But as such, so you have vector of probability. So it's in a way, so you have a probability distribution of this number of variables, and you want to compare it with another probability distribution. For this purpose, so in the probabilities domain, so you have this special distance measure. Again, so cross entropy is nothing more than a distance measure between two probability distributions. Or rather, maybe it can be formulated as the measure of dissimilarity. Between two distributions. So we have the normal, I mean, if you just read this in probability, so normally you have distribution P, and distribution Q, and you want to compare how similar are these distributions. So in our case, P of X is the distribution of predicted labels. So labels, and obviously Q is no, sorry, it's no, not predicted. So just to be consistent with my own notation. So so P would be the probability of true labels. So that would be our classes. C, I, and Q is actually distribution of predictions. And how did we denote them? We denote them as P. So our P i's. So on this figure, I mean this outcome PIs should be compared to true labels C1 to CN. So, but now, saying that, so we need to define the function itself. So the cross entropy, so these two distributions. So for a given sample, so now we have a distribution of a true label, and again, so as I said, so this is a little bit artificial interpretation, I would say, because in one hot encoding, so this distribution is very kind of special. So you have one in a single position and zeros in all other positions. So, but nevertheless, this measure the cross entropy between the distribution of labels, between the distribution of true labels and the predicted labels, is this function over here. So you take so minus ci logarithm I plus, and well, I write it on purpose because if you sometimes I mean during presentation in some sources you see shortcuts, but that's what I mean kind of unspelled out version looks like. So it's like minus then 1 minus c, and the logarithm 1 minus c. So this is it. So in or that's what you see normally in the final form. So you have minus some. So for all, so that was for particular labels. Then for all labels for all classes for C and all predictions. So you you have it. So you just sum up all this measures CI ln PI plus 1 minus CI ln 1 minus PI. So this would be your cost function. So, so what? But I mean, now we come to an interesting thing. So let's put all the things together. So we have our axis, and again, so we have this dummy activation functions, and so we have some. So I skipped all the hidden layers. So we have this yes. So this is these are our scores. Score 1 through score 10. Then so we do this normalization. So we input them into softmax, and we have so P1 as so X of, so let me see. I probably will reuse this X here instead. So we have X1, I don't know, X M. So X1, so softmax P2 S X2, let's see, EM, that's M. So now we have this probabilities, and now we have this cross entropy cost function, to which we input on the one hand, so all this probability is going, and on the other hand, so we have this true ground. So for the 0, say 1, 0. So this is the whole thing. And what this guy does, so it spits out an error. Or cost. But this is the mismatch. So the measure of mismatch between the outcomes of computation and what we want to have at the out. So what we what we want to do, we use this error, and so we want to compute. So this is the so denote it as E. So we computed the E. So at the end, so we want to compute the E by D score. So that's what we want. So we take this error, or this function, and we are interested. So how to change the inputs to this softmax, so that we make us closer to the desired labels here. So to reduce the measure of dissimilarity. Yes. But then, we have the softmax on the way, and what we do first, to spell it out, so we do first we compute the derivative of this error with a function with respect to this piece, so the pi's, and then we compute in the next round, we compute dpi's with respect to d score. So it's a so we apply a chain rule. So we apply a chain rule, and what is the interesting thing is the following. So I will skip the intermediate steps. And let me show you one interesting thing. Yes. First, this guy over here. So this is the derivative of the cross entropy function. So this is with respect to output of the softmax function. I think I unnecessarily renamed this function. So that was h before, and that was also h. So, and that one is also h. So dh with respect to dp. So and h is you remember that with logarithm and such. So I will just spell it on the first line and the last line, and jump onto the last line. So it's minus sum ci logarithm pi plus 1 minus ci logarithm 1 minus pi. So that's kind of complicated function, and now we want to take a derivative with respect to pi over here. So if you do this, well, I have 1, 2, 3, 4, 5 intermediate steps. So you come to the following result. So that this derivative is minus ci divided by pi. So no logarithms. That's good. Plus 1 minus ci divided by 1 minus pi. So this is the derivative of the cross entropy function with respect to the values at the end of the to the result of softmax. Right, but now we want to multiply it with the derivative of the softmax function with respect to the input to softmax function. So because it is these inputs we want to try to tune. So we want to compute the gradient for these inputs. And so this one we computed before. So so the derivative of softmax, so which takes certain input xj and with respect to specific well, the partial derivative with respect to other inputs, say xk is equal to x s j 1 minus s j. So it's for the case j equals k. And the second thing is for the case when j not equal to k. So, but what we up to here, so we want to compute this derivative of the outcome of the softmax with respect to a specific score. So we are considering this very case over here. So when these axes are same, and in this case, so our derivative. So now in terms of p's is p I1 minus p I. So we just take whatever values we have as an outcome of softmax function, and so the derivative with respect to specific score looks like this. So now we want to combine these two. So we at the end we wanted to compute d h, so which is the this cross entropy. With respect to specific to a particular score. So, and that was we applied chain rule. So and it looks like that. So dh dp. So that's the output from the softmax multiplied by dp. So with respect to d score. Right. And so now the math is very simple because this guy over here is like this, minus ci pi plus 1 minus ci 1 minus pi. So that's this thing. And then you multiply it with this thing right here, multiplied by pi 1 minus pi. So now if you do this simple multiplication and open up the parentheses, what you get is that this derivative is actually equal to pi minus DCI. That's really cool. I would say, because it also kind of creates a mental pitfall, I would say. So if you would look at the implementation, some kind of calculations are missing, obviously, there. So somewhere in the big, in the implementation of the backprop function, so for the very last layer, so you see only well, you see this result over here, and it is so kind of tempting to believe that what is not evident in this implementation in lab 5 is what kind of post function is used. It's never spelled out. It's never spelled out in commentaries, and I left it like this on purpose, because I mean, when I was parsing this, so now I'm telling you my way, but I hope you also can follow the same path. So when you parse the implementation and look how the backprop is implemented, so everything looks very logical. So in the very beginning of the implementation, where is it? In the very beginning of the implementation, so you choose an activation function immediately in that implementation. So you see clearly, okay, this is the derivative, so it will be used on the backward path, and then you really find this place in the code. But then you clearly see how computation is done layer by layer. But then at the kind of very last layer, so the only thing you see is actually this result. This result over here. And as I said, so it is so tempting to see that, I mean, so when you come to the last point, so you computed the scores, so your error function is simple, the difference between the labels that you use for backpropagation. So that, I mean, I had this, I had this mental kind of trap, and throughout years, believe me, so I mean, when I had this verbal assessment, so basically all suffer from this understanding. So that when you go to the last stage, so you just compare whatever outcome your softmax function gives to true labels, and what you propagate back, I mean, to set the weights in the learning process is simple difference. So that's not a simple difference. So this is a derivative. So, and that's what I mean, what is the purpose for me to kind of spend all this time with this clarification? So this is a derivative of a cost function, which is cross entropy, with respect to the output of the softmax changed with the derivative of the softmax with respect to particular input. Then it mathematically makes sense to propagate this this value, which is really the difference between kind of the one hot encoded vector and the output of softmax. So the to set the to compute the gradients. Yes.
When do we get isn't that basically the direction? And then we use the loss, the step to go that direction. Right?
Yes.
Right. So the derivative is actually the direction of the error.
Absolutely. Yes, that's true. Yes, that's the whole thing with the definition of gradient. So gradient shows the direction towards minimization of the function. So the thing is that I mean, again, so to me, this links to neurons is a little bit misleading, actually. So and that's why I prefer to talk about multilayer perceptron. Really, I mean, from the standpoint of view of a function of function. So it's just a complex function of many variables, and this function is differentiable. And it makes sense only with the differentiable and convex cost function. So because that is what you optimize. So the only thing you want to minimize your cost function. And as such, so your cost function should be, well, convex and differentiable. And it can be anything, as I said. So the only thing, so if you would, for example, be given this lab 5 code, and now I say, okay, modify the code such that your cost function is mean square error. Then you should know that you should modify basically the place where it is currently written this thing. So like I mean, on a very final stage. So you need to basically repeat all the steps of taking derivative of the score and of your target cost function with respect to the scores. Not necessarily that you need softmax in between. So you can simply just do this computation. That's totally valid. But again, so it is not necessarily that you will come up with this very simple simple result for computing derivative. And personally, I find it really kind of amusing to track this kind of complex concepts like you know, cross entropy, which is complex function, softmax, which is another complex function, which boils down to this very simple derivative. And yeah, so that's basically my message. And again, I find it useful really from the understanding of processes, what is going on inside. Really just checking the implementation, but then trying to find explanation. So why the programmer choose one or another implementation. Yeah, and that is what I wanted to tell you regarding MLP. So maybe it was, I mean, same, but maybe a little bit different, at least with some details. And personally, I also found that so this information exists in the internet, of course, but it's kind of scattered, so it's hard to kind of put everything in one place. So, and probably you may at least be inspired by these scribbles if you need to kind of restore for yourself. That's the reason. Okay. Good. Any questions on this? No? Then we continue next week with the time series. Okay. Thanks. Yep.